Welcome to this video. We're going to learn about something called resistivity. Resistivity, as a general overview, is the inherent resistance of a particular material. Okay, when we look at circuits, we say ideal wires do not do anything to the circuit except transport charges from one spot to another. The potential difference across an ideal wire, the energy the wire consumes per coulomb of charge passing through it, that potential difference across an ideal wire is 0 volts, 0 joules per coulomb. And the reason is because ideal wires have a resistance of 0 ohms. They don't dissipate energy, they don't supply energy, they just carry the charges. But in reality, this is not how things really work. In the real world, wires have some resistance. Now typically this resistance is so small, the wire resistance is so small, we can ignore it. We say it's negligible. It can be ignored. The resistance of a wire, though, does depend on some other things, so you can make the resistance really small by looking at what impacts that resistance. The three things are the wire's type of material. Some materials are inherently more resistive than others. Also, the wire's length impacts its resistance. We'll see that longer wires have more resistance, and its cross-sectional area. That's like if you cut the wire in half, how big is the face that you're looking at? Different materials have different, inherent resistance is sort of what we want to say, but instead of saying inherent resistance, we say different materials have different resistivity. Resistivity, that's the property that measures how inherently resistive a material is. We give it the Greek letter rho. It's like a fancy P. The equation for resistivity is, well, let me give you this equation first. The resistance of a wire is equal to the resistivity times the wire's length over the area. We often rewrite this equation by isolating rho, and then you would have R times A. A comes up to the numerator over L. We're going to look at that equation here just in a moment. The units of rho, the resistivity, are equal to the units of resistance times the unit of area over the unit of length. Resistance has units of ohms, area, meters squared, length, meters. One of the meters getting squared here cancels with that meter in the denominator, so the unit for resistivity is just the ohm meter. Let's take a quick look at this equation and what it means. Here are two wires. Now the length of the wire is just this distance here, right? That's the length of the wire. Let's give it two arrows, make it nice and thick. The cross-sectional area is the area of this open face. When you cut the wire in half, that area right there is the area of the cross-section. So which of the two wires has a bigger resistance? Well, let's say they're the same material, so rho is the same for both. One of the wires has a bigger area than the other. This wire has a bigger area, and so it's dividing by a bigger value. The area here is maybe 5, down in this case. So you're dividing the numerator by 5. But up here, the area is smaller, so you're dividing the area by something like maybe 1. So the bigger the area, the smaller the resistance. They're inversely proportional. What about this type of case? They have the same cross-sectional area. This face has the same area as this wire on the bottom, two different wires, but the length is not the same. So which of them has a bigger resistance? The bigger the length, the bigger the resistance. Why is this true? Why does the top resistor have a larger resistance than the bottom? Well, imagine you have a bunch of charges that you're trying to cram through. All these charges come out from the battery, and you're trying to cram them through this tiny little narrow passageway. And so, because the passageway is so narrow, there's like a bottleneck effect, kind of. And so the resistance is higher. On the other hand, if the passageway is not so narrow, then those charges don't have as much trouble going through. That's kind of the idea. On the other hand, if we're down here, right, when the length of the wire is bigger, those charges get bumped around through a larger distance. And so the resistance is bigger because they have more resistor to travel through. Each individual charge has more resistance to travel through, and thus a larger resistance. On the other hand, when you send the charges through a smaller wire, you send them on through, and each individual charge has less resistance to get through because there's a smaller wire. So that's why L decreases the resistance when it's a smaller length. We're going to finish up by solving number 1 from the handout. A copper wire of electrical resistance R has a length L and a cross-sectional area S. Another copper wire, same material, same resistivity, has a length 2L and a cross-section area of S over 2. What's the resistance of this second wire in terms of R? So we simply write down the resistivity equation twice. The equation says resistance is resistivity, resistance equals the resistivity times the length over the area. And we're going to write this equation 2 times, once for the first wire, a second time for the second wire. So in the first wire's case, the resistance, we're calling that resistance R, and in, the length is L. L is in the denominator. The area is S. So let's make up a variable for the resistivity of copper. I'll just use rho. In the second case, we've been told the length is now not just L, it's not the same length. The second one has twice the first's length. So this is 2 times the first wire's length. And the cross-section area is S over 2. So the area here is not the same as the first wire's area. It's only half of this first wire's area, S over 2. And it's copper. They're both copper, so the resistivity is the same. They did not give us a variable for the second wire's resistance, so I'll just call it R2. I can't call it R because that implies that the 2 wires have the same resistance, and that may not be true. So instead I call it R2. Let me get rid of all of these other values that we've added in. Move those all out front in front of the variables. And when we do that, what do we get? We get R2 equals, well, there's a half in the numerator, and then there's another 2 in the denominator, so it's 2 times 2 down here, times rho S over L. But rho times S over L, this whole thing, is equal to the first wire's resistance, R. And so what we have is R2 equals 1/4 of the first wire's resistance, R. And that is our answer.